Hi, everyone. My name is, as mentioned, my name is Akshat Tandon, and I basically lead all the quantum machine learning activities at Airbus here, Central R&T team. And yeah, and first of all, I'd like to thank Q2B to give me this opportunity to talk about our quest to enhance AI for aerospace data analysis. But before we talk about the case study, let me brief you a little bit about where exactly this all fits in within Airbus ecosystem. So as we all know, quantum technologies are transversal technologies. So of course, Airbus is exploring all the pillars of it. We are heavily engaged in quantum communication. We are working in quantum sensing, and also my talk will be focusing, of course, on quantum computing. So you'll see what we are all doing in quantum computing specifically. But if you have interest in quantum sensing, there will be another talk by my colleague, Dr. Jasper Simon Krause, in the sensing track. So maybe you can see what all the interesting work we are doing in quantum sensing as well. So to understand the requirement of quantum computing for aerospace, we first, of course, need to also understand what is indeed the requirement to have high computational capabilities or high computational performance capabilities in the aerospace domain. So as you can already imagine, airplanes are not anymore just some bunch of mechanical parts flying around. They consist nowadays a lot of sensors, so approximately more than 200,000 sensors, making aerospace one of the most data-rich and data-dependent industry. And thus, of course, to analyze that kind of data, and to use that data, we need high-performance computing infrastructure. So we basically, thus, we have our own HPC systems in Airbus. And we're also aware that classical computing might reach their limit in the future. So we are also exploring other options. And of course, quantum computing is one of them over there. Our KPI over here is that we can indeed apply quantum computing to a relevant business application in operational environment for our customers as well as for our products. And of course, as I say, like Airbus and aerospace as a whole has a lot of these key application areas where we think quantum solutions can help. So because there are so many of them, so we cluster them in four families or four categories. In quantum simulation, we basically focus on application use cases related to chemistry simulation, for example, or energy system modeling, and etc. In quantum optimization, it's related to optimization related problems. In solvers, for example, we are trying to use wherever we are trying to use quantum solution to improve CFD simulation, for example. And in quantum machine learning, of course, there are other bunch of various use cases from data anomaly detection to basically multi-agent reinforcement learning. So of course, we understand that it's a huge exploratory space. And of course, we have like a lot of key application areas where we want to implement quantum computing. But we also realize that the fastest way to do that indeed would be to develop these kind of partnerships. So we do that a lot with startups, with academia as well. And my talk, the case study basically for today will be one of such collaboration with QCware, where we developed a quantum enhanced anomaly detection algorithm. And with the same motivation, last year, in collaboration with BMW, we launched a quantum mobility quest. So it's a quantum computing challenge. In this, we divided this into, we basically gave the community 5 different application problems or challenges divided in 2 tracks. In forward track, we basically give the participants some of the very interesting business applications where we feel quantum computing can provide a solution, or at least had a potential to do that. And then there is a reverse track where the participants can actually reach out to us and basically provide some kind of solution to some problem that, or some application which they seem would be interesting to solve. A glimpse of the timeline of this challenge, by the way, just for information. And it will be divided into two phases, by the way. So phase one will include submission of technical solutions from the participants, and phase two will basically include then shortlisted participants will basically implement and demonstrate their solution. So if you have interest in this challenge, and if you are not yet registered, I'll recommend you to basically go via this QR code to the website for the challenge and register it. We already have a lot of participation, and just to point out, the final deadline for phase one will be in April end, so it's coming soon, basically. So now coming back to our use case or the case study itself. Anomaly detection over here for aerospace is one of the one field where basically have a lot of vital applications. So for example, if you look at the image on your right, for example, it shows basically, no, on your left, sorry, would be basically an image of which basically shows you the the trajectories of all the ships and vessels in the sea. And anomaly detection, for example, can be used over here to predict abnormal activity behavior or like illegal activity in the sea. The same or similar application of anomaly detection could be basically in defect detection for material science. For example, in the image on your right-hand side, you can see a CT scan of a 3D printed part, where anomaly detection can be used basically to predict defects or abnormal structures. So with the same intention, and with the focus on maritime surveillance anomaly detection use case, we collaborated with QCware and to develop basically an anomaly detection algorithm. And what you see over here in the black is basically the input images that we used for this use case. So basically, the idea was to capture the trajectories of all the vessels in a particular geolocation, and then use this in an autoencoder structure to basically predict anomalies if there are any. And a typical solution for such anomaly detection problem could be an autoencoder structure. So basically, classically, we are doing this for ages now, where what we try to do is basically we try to take this input image, encode it into a very low-dimensional vectors representation, and then we use a decoder to basically reconstruct from this small vector representation the complete image. And then basically we try to force the network to learn to reconstruct the images without any error. Now, assuming that the non-anomalous images will be will appear with comparatively very high frequency as compared to the anomalous images. So what we can assume over here, that the features that will be learned by the encoder will be mostly non-anomalous features. So that means basically that if we pass a non-anomalous image to this autoencoder structure, it will be able to recreate it with less amount of reconstruction error. And if by chance we replace this with an anomalous image, because now it did not learn, or it did not learn to encode the anomalous features of these images. So of course the decoder would not be able to recreate the anomalous features in the recreated or reconstructed image. So thus this will result into a very high amount of reconstruction error. And there are various like versions of this kind of algorithm. One of them is indeed where we introduce orthogonality to them in classical domain as well. And the reason that we can add orthogonality over there will benefit us is that we could basically learn more efficient features in this bottleneck part. But of course, in classical domain, orthogonality is expensive. So you have to either use some kind of regularization or something like that to basically introduce orthogonality in the weight matrices. So our work included. So what we did here was we replaced both the encoder and the decoder part of the autoencoder with a quantum circuit, And to introduce the orthogonality over here, which will basically for us will be free if we use this kind of pyramidal quantum circuit, which is also work previously done by QCware, by the way. So this kind of structure with circuits basically will automatically introduce orthogonality in the weight matrices. And this basically is what we are using in this let's say, quantum enhanced solution. And when we used it, so what did we see is indeed some impressive results. We were able to detect, of course, all the natural anomalies as compared to the classical ones. So the ones which were detected also by the classical approaches were also detected by the quantum enhanced approaches. We were also able to detect far more better the artificial anomalies. So quantum enhanced solution, in some sense, showed more robustness to the artificially generated anomalies. So some of the images over here is just some kind of anomaly we artificially created. And so the more main important part basically over here is the graph below, which basically in some sense tells us that there's not much of a difference in the performance, but at least we see some better performance in the quantum enhanced solutions compared to the classical ones with the same complexities. So in the previous, like this circuit and the algorithm that we used, we still see some of the anomalies which were not detected by that algorithm. So what we did then, we then think of using Bayesian neural network over here. The reason basically would be that we would estimate the uncertainty of these predictions and basically try to just remove the predictions from which have very low amount of confidence from where the network is very low in confidence. So basically improving the accuracy over there. And how this movement from standard to Bayesian neural network looks like is, and how is it different is, so in standard neural network, basically we are learning a point estimate of weights. But in Bayesian neural network, we basically are trying to learn the distribution of these weights. So what we can do is we can sample, let's say, 100 of these weights and basically predict 100 times the output. And then we'll have kind of a distribution of the output as well, so which can be used to detect, let's say, the some kind of confidence score of the network prediction. So if it is if the variance is too high, we can say the network isn't sure about the prediction, for example. And yeah, of course, if you want to introduce orthogonality in BNNs, it's in classical domain. It's very difficult because it's even further difficult than the classical domain. So now we need to sample something from a distribution, and then we have to somehow orthogonize that, and which is very costly, basically. So what we felt, and as we did also in the classical, in the quantum enhanced convolutional neural network, we use the same pyramidal quantum circuit and basically try to remain in the orthogonal space itself, or orthogonal group itself. And basically we get orthogonality in some way for free. So in conclusion, what we found out with this case study was that quantum enhanced methods indeed potentially performed similar or better than their classical counterparts with similar complexity. And we also learned that using quantum enhanced Bayesian methods, we could actually predict anomalies or non-anomalous images with higher confidence from the network. So that will be it from my side.